So let's begin. What we'll do is for these three topics, electrochemistry, then colligative properties, and then for kinetics, we'll want to one by one populate all formulae, all results, all the graphs and all, which we are supposed to do. Let's begin with electrochemistry first. I hope my voice is loud and clear. We're going to get started with electrochemistry first. Now, in electrochemistry, please hear me out. In electrochemistry, the three subtopics are conductance, naturally potential, which involves Nose's equation and all, and then you have Faraday's law. Let's begin with conductance first. And right away, when it comes to conductance, I do tell you, it's basically the reverse of resistance. One by one, we'll want to populate all the formulae and all. Now you begin with R is equal to rho L by A, and I told you there is nothing like capacitance measured by any instrument. It's basically the resistance which is measured using a Wheatstone bridge. You know about resistance, R is equal to rho L by A. Now 1 by R naturally will look like 1 by rho into A by L. I'm taking the reverse of it, and I'll arrive at the formula like conductance is equal to 1 by rho is called kappa A by L, and this is going to be more relevant. Trust me, this is going to be more relevant. Kappa is equal to conductance into L by A. This is going to be the first significant formula where kappa, is called specific conductance, or what's another name for it?
Conductivity.
G star हो जाएगा.
Certainly called cell constant.
G star.
For some reason, we prefer CGS unit here. So here the unit will be per centimeter. This being length, this being area. This is per ohm per centimeter. This is per ohm per centimeter. This is per ohm. I'm sorry. This is per ohm. Also written as MHO. At times written as Siemens. So because conductivity, conductance, the terms could be a little confusing. I'll always want you to go by the unit. So the unit of kappa, is if this is per ohm and this is per centimeter, per ohm per centimeter. I told you these are things I would have done in the class, but maybe for the sake of it, you'll just want to quickly go through all of it. Let me know if there is something which is new to you. Let me know if there's something which is a doubt. Generally, cell constant is a constant because it will be about the electrochemical cell where the measurements could be taken. So to be on the safe side, we'll want to go with the unit conductivity per ohm per centimeter. Yes, we can move on. Next formula is certainly about molar conductance. Now, molar conductance, which is due to conductance of all the ions per mole, would be very popularly represented as kappa into 1000 by m. I hope you remember this form. Now, 1000 by m is when m is the molarity. 1000 by m when m is the molarity. Realize, if this is, if one thing which I do tell you, always remember kappa as the conductance per mole. This is going to be such an important particular approach. Always remember conductance per ml. Kappa is conductance per ml. Kappa can be written as conductance. Naturally, if L is equal to 1 and A is equal to 1, this is centimeter square, this is centimeter. So if there is a unit cube, filled with the electrolyte, and that unit cube filled with an electrolyte, where L is equal to 1 centimeter, the distance between the electrodes, and the area is 1 centimeter square, it will be holding 1 ml, 1 centimeter cube, which is 1 ml of the electrolyte. So kappa is equal to conductance per ml. This is going to be such an important concept. I repeat, kappa is conductance per ml. Kappa is conductance per ml. So if this is conductance per mole, I could always represent this as some volume, which is volume per mole. Volume per mole. Yes or no?
So ये 1 centimeter cube मतलब per ml वाला कैसा है वो आप समझा सकते हैं?
मतलब अगर कप्पा को डिफाइन करना है स्पेसिफिक कंडक्टेंस, जैसे मैं बोला था ना, इट कैन बी डिफाइंड एज द कंडक्टेंस पर एमएल.
Yes.
You'll kind of recall you defined resistivity and resistance of a unit cube. Resistivity, before class 11 was the resistance of a unit cube. Yes or no? Yes or no?
सर पर centimeter cube कैसा है हम समझा नहीं.
I mean, you remember resistivity and resistance per cube of a unit cube? This was resistivity, specific resistance. L is equal to 1, A is equal to 1 centimeter square. The resistivity was resistance of a unit cube made of that material. Yes or no? Yes or no? Grant.
Yes.
But some classmate, class करना है तो आ जाओ. Can you hear me? I hope you're understanding me. I mean, Grant will want to respond. Will you want to move on? This is
Yes, sir.
resistivity because of before class 11 is resistance per unit cube. So how do you go for specific conductance? Specific conductance is conductance if L is equal to 1 centimeter, A is equal to 1 centimeter square. Basically, you imagine a unit cube. You imagine a unit cube. You know, unit cube is where L is equal to B is equal to H. All are 1 centimeter. This is 1 centimeter. This is 1 centimeter. This is 1 centimeter. So naturally, if this is one particular wall, and if this is the opposite wall, and if these two are connected to a battery, and if the distance between the two is 1 centimeter, so the area of the area of the two opposite walls are acting like the cathode and anode. And what's the amount of electrolyte which is filled in this unit? It's about, here L is the distance between the electrodes, A is the surface area of the electrodes. So if I assume it to be a unit cube where two opposite walls are made, uh, naturally the area is 1 centimeter square. Yes or no? This is 1 centimeter square. So if I take the opposite walls as the two electrodes separated by distance 1 centimeter, this is what I mean. L is equal to 1 and A is equal to 1 centimeter square. This is the distance between the electrodes, is the area of the electrode. So the electrolytes filled in this unit cell will be 1 ml, 1 centimeter cube. That's the volume of the electrolyte. Yes or no? Girls will want to respond. Rest of you would want to respond for me to move a little faster.
Yes, sir.
So, this is such an important concept. It's such an important concept. I don't remember if I taught conductance in your batch or not, but, every person who has been in my class in conductance, it's very important that on day one I tell you, this is taken as conductance per ml. This is taken as conductance per ml. Everything which you learn about specific conductance decreasing with dilution, is based on this premise only. But chalo, हाँ ना बोलो, kappa from day one is conductance per ml. For a given concentration, kappa is conductance per ml. Molar conductance is conductance per mole. So don't you think conductance per mole would be eventually conductance per ml. This will be conductance per ml into some volume, which is like volume per mole. So conductance per ml into volume per mole would be conductance per mole.
Yes, sir.
So from day one, it's imperative. Hardik, I think you can hear me loud and clear. And if somebody else has taken your class, I mean, Abhishek, people from Full Bagan batch, please respond. I think, this is understood. Kappa is equal to conductance into L by A. Kappa is equal to conductance when L is equal to 1 and A is equal to 1 means, this is the distance between the electrons and this is the surface area of the electrons. So I'll draw a unit cube. I'll believe the opposite walls of a unit cube are like 1 centimeter square each, acting as the cathode anode. And in that case, the cell, which is a unit cube, would have a volume 1 centimeter cube. So this is defined as the conductance per ml. This is extremely, extremely important. Everybody, if you have not known it in the past, you want to take a note of it. Kappa is conductance per ml. Kappa is conductance per ml. The molar conductance is conductance per mole. This is conductance per mole. This is conductance per mole. This is conductance per mole. And kappa is conductance per ml. So don't you think kappa, which is conductance per ml, into the volume per ml, volume per mole, volume in ml per mole. This would be a little new to you because we are generally used to finding number of moles per liter. But I keep on saying volume per mole. If you are able to interpret it, if this is conductance per ml and this is the effective volume, if it is the effective volume containing 1 mole, it's the effective volume containing 1 mole. I told you molarity m का मतलब होता है there are m moles in 1000 ml. So naturally ml per mole, 1 ml, 1 mole, if m moles, which is the molarity m, are there in 1000 ml, so 1 mole is effectively 1000 by ml. Please respond. Please contest if you have any doubt. I can write it, maybe one more time. Molar conductance is conductance per mole. This is conductance per ml. And this is the volume in ml per mole. So if this is per ml, and if this is volume per mole, this would eventually be conductance per mole. Yes or no?
Yes, sir.
This VML turns up to be 1000 by m. This VML turns up to be 1000 by m for a solution which is m molar. For a solution which is m molar, you'll have m moles is 1000 ml, so volume per mole will be 1000 by m. Again, this in volume eventually will be in centimeter cube. This will be in centimeter cube. You have known kappa as Siemens per centimeter or per ohm per centimeter. Again, to be very honest, this will be centimeter cube per mole. So the unit of molar conductance, and always go by the unit, would be Siemens centimeter square per mole, or it would be like per ohm centimeter square per mole. The units are going to be very important in this topic. I think you're happy with this. We'll want to move on.
Yes, sir.
Something which you find for molar conductance, you do exactly the same for equivalent conductance. Now, equivalent conductance would be kappa into 1000 by n, where naturally n is the normality. And by now you realize this time it's going to be the effective volume holding one normal of the solution. Again, if the solution is n normal, you'll say there are n equivalents in 1000 ml. So there is going to be one equivalent in 1000 by n ml. So this is basically going to be some volume, say VML prime, which is the volume per equivalent. This is the volume in ml per equivalent. This is the volume per equivalent. This is conductance per ml. This is conductance per ml. This is volume per equivalent. So this eventually would be conductance per equivalent. This would be conductance per equivalent. Yes or no? The relationship between this molar conductance and equivalent conductance would be again the very popular N factor I keep on talking about. N factor, which is the ratio of molecular weight by equivalent weight. I hope I'm being understood.
Yes, sir.
Which is also the ratio of, if I maintain m and n here, normality upon molarity. We'll want to move on. बच्चे लोग खाना बोलो.
Yes, sir.
So maybe one quick time, and trust me, it's important. Maybe one quick time, it's important. One, kappa is equal to conductance into L by A. This is cell constant per centimeter. This is Siemens or per ohm. MHO is also unit. This is per ohm per centimeter. Very, very important. Kappa is conductance per ml. Kappa is conductance per ml. I think I have made this clear to you now. And then when you arrive at molar conductance is equal to kappa into 1000 by m, so many times you'll want to write molar conductance in terms of conductance. So many times they'll give you the resistance. So 1 by resistance is going to be required. And get used to this extended form as well. This is n normality. Now this is Siemens per centimeter into centimeter cube, which will become centimeter square per mole. Now this will be Siemens centimeter square per equivalent. I think I'm being understood. This is the so-called N factor, which is molecular weight upon equivalent weight. And in terms of molarity and normality by molarity. Now, this is another fact. A value of molar conductance upon what is going to be called infinite conductance. I'm teaching class 11 guys, Ostwald solution law right now. First time I tell you Ostwald solution law, concentration tending to zero or at infinite dilution, all electrolytes behave like weak electrolytes, till all ionize completely. Naturally, conductance is a property of the ions, the number of ions. So this upon, the maximum value, this certainly is going to be called the limiting conductance. Some textbooks are going to call it limiting conductance. And put a knot here. I particularly write infinity here because I mean this is an infinite dilution. Limited conductance is an infinite dilution, which I repeat is hypothetical but relevant. This will give you the value of alpha. So many times here talking about an acid or a base, Ka or Kb will be C alpha square. So get used to all these results. Get used to all these results, and we'll want to move on. We'll want to move on, but it's obviously a recall of with dilution, number of ions increasing and conductance increasing. With dilution, number of ions increasing and conductance increasing. A very popular plot is when you draw conductance versus root concentration, you get two types of curves. All of them are for strong electrolytes, where alpha is almost equal to 1. Can you tell me very quickly, for alpha equal to 1 at all concentrations, these graphs, when you plot conductance with root concentration, first of all, you're going to plot these graphs in the negative direction of x. You keep on diluting it. You also understand they'll never touch the y-axis. They'll never touch the y-axis because you can't have zero concentration. Yes or no? Please hear me out. Something like this would mean they're strong electrolytes, and something like this would mean they are weak electrolytes. For weak electrolytes, it's going to abruptly increase as it comes closer and closer to the y-axis. So, increase in the value of conductance, the increase in the value of conductance, this is delta M or delta A does not matter because they are proportional. Increase in the value of weak electrolytes as it closes in is imperative because, at very dilute conditions, the number of ions will increase abruptly. But what at all makes strong electrolytes, have their conductence values raised? इसका अगर थोड़ा सा भी पॉजिटिव होता है, ये हल्का सा भी ऐसा क्यों होता है? Even if it's a straight line almost normal to the it's parallel to the x-axis, why is there at least a little bit of slope? Why does it increase at all? Will you tell me quickly? I mean, these are things I thought most of you will have on your fingertips. You have your board exams around the corner. It's not like you're not able to understand me. It's not like you don't understand this is for a strong electrolyte and this is for a weak electrolyte. This is imperative because here number of particles will increase abruptly. But what about this one? Strong electrolytes, what about this one? I hope I'm being understood. There is a small little, slope here. Why at all is there going to be a slope? I hope my voice is loud and clear. I hope you're understanding me. I hope there is no apprehension in responding at your end. We're killing time otherwise, Just taking us nowhere. I'll start calling you by name. So one by one. Abhishek, why is there a positive slope at all for strong electrolytes? Arpit, Dheeraj, Grant, Jatin, Kosto, Ratrisa,
Yes, sir.
Siddharth. So you want an answer from me? Yes, Ratrisa, go ahead. Yes, Ratrisa, go ahead. I hope I'm being heard. I thought I interrupted you, Ratrisa. You want to quickly answer this so that we can get back to work.
Sir, can you
Why
repeat?
at all? I mean, why at all there is a slope here? You understand this is almost parallel to the x-axis. With dilution, it changes very, very barely. This is for a weak electrolyte where the number of particles increase. But why at all there is a slope here? Naturally, the number of particles will not increase. Naturally, the number of particles will not increase. It's going to be alpha is equal to 1 at all concentrations. I hope I had told this. I hope some of you know it. I just don't know why you are, so reluctant to reply. Now, eventually, I'm telling you, although I guess some of you would be knowing it. There is some slope. There is some slope because although alpha remains constant, number of particles remain constant with dilution, with dilution, certainly interanic electrons, interanic attractions decrease. So it's like, with dilution, the traffic is clearer. The traffic is clearer. The traffic is clearer. The traffic is rarer. So, the same car can move, obviously, in a clearer traffic without any interactions, lesser interactions, with more. See, eventually, conductance is about the ease of flow of current. And the ease of flow of current will depend on two things. One, number of particles. That is the case primarily for weak electrolytes when the number of particles increase. Two, naturally, this is going to be a smaller factor. And this smaller factor is the only factor for strong electrolytes, where with dilution, naturally, because the interanic interactions would be lesser, the same number of particles would move with, more alacrity. Yes, we can move on. बच्चे लोग खाना बोलो. This can't be obtained naturally. This infinite conductance is only hypothetical but relevant. But there is the maximum, also called limiting conductance. And I would have told you in the past, this is obtained by extrapolating this delta M versus root concentration for strong electrolytes only. Strong electrolytes only. This can be done only for strong electrolytes. Only this can be extrapolated. Only this can be extrapolated. Only this can be extrapolated. This can't be extrapolated. You don't know where it's going to go. This is like you don't know. This can't be done. For a weak electrolyte, you don't know where it's going to go. For a strong electrolyte, you can extrapolate it. For a strong electrolyte, you can extrapolate it. For a strong electrolyte, because it's behaving in this manner, maybe if I zoom it in, and this can be extrapolated because it's behaving in a particular manner. But something which is like going in this direction, you don't know it's going to go here, it's going to go here, it's going to go here. So this extrapolation can be done for strong electrolyte, can't be done for a weak electrolyte. So the infinite conductance, the limited conductance can be obtained by extrapolation of the conductance versus root C curve only for a strong electrolyte, not for a weak electrolyte. For weak electrolyte, the only way is from Kohlrausch law only. Now, I don't have enough time to talk about Kohlrausch law. I'll simply give you the result, which is at infinite dilution, Naturally, it goes without saying at infinite dilution, because these are going to be infinite dilution cases. For a weak CFCCOOH, you might want to take CFCCOONA, HCl. This will give you acetate. This will give you H plus, and you can subtract NaCl. So basically, at infinite dilution, this is the sum of acetate plus H plus. This is the sum of acetate plus H plus. This is the sum of H plus and Na plus. I'm sorry, H plus and Cl minus, and this is the sum of Na plus and Cl minus. So naturally, these values could be obtained by extrapolating that graph because they are strong electrolytes. This cannot be obtained. This can be indirectly obtained using Kohlrausch law. Naturally, because this plus this would be eventually the sum of the ionic conductance values, and all the ionic conductance values would be independent of the counter ion. The value of acetate would be the same whether it's with H plus or with acetate, with sodium or potassium. H plus remains the same whether it's with acetic acid or with Cl minus. H plus OH minus and water will have particularly high value of conductance, that's called Gauss's conductance. I have given in the video how they're going to do jumping act. I want to not go there because that's not relevant for the board exams. Now, this value of conductance, this value of conductance of the individual ions and you can get what's called the transport number of the cation and transport number of the anion. Now, transport number of the cation would be this, the thing, which is like the transport number. Just in case I did not mention it in the past, please take a note of it. Transport number, the two would act to unity. This would act to unity. Is about uh, the conductance due to cation and the conductance due to anion. So, this is going to be the ratio of the ionic conductance value or the total conductance of all the cations upon total conductance, which in this case is total conductance of all the anions, and the total conductance. Naturally, because it's about the cation and anion, eventually carry charge. This is going to act to unity in a given problem. It's the cationic transport number. I'll tell you the name. It's called transport number. So the transport number due to a cation, in a particular electrolyte is 0.45. You can safely believe for anion it's 0.55. Yet again, it's going to depend upon the amount of charge carried, and the amount of charge carried would be proportional to, the ionic conductance values. So this is all I have to tell you. We want to move on.
Can you just wait 1
कभी
minute?
कभी ionic conductance बोलता है, कभी कभी ionic mobility बोलता है. Yes, नहीं?
So just 1 minute and noting.
I think I already told you the value of alpha is obtained. This is something again you'll want to keep in mind. कि कभी नॉट रहता है, कभी इंफिनिटी रहता है, एक ही बात है. नॉट इंफिनिटी एक ही बात है. I think I did tell you this. आगे बढ़ते हैं बच्चे लोग, आगे बढ़ते हैं.
Yes, sir.
Now the second portion of conductance, second portion of electrochemistry is naturally Nernst equation and the laws and all. So very quickly, E naught cell is equal to E naught oxidation potential of anode and E naught reduction potential of cathode, and the one which is having higher oxidation potential, would act as the reducing agent, and the one acting as E naught reduction, if the tendency to get reduced, and the one getting reduced would actually act as oxidizing agent. Now, the one acting as an oxidizing agent, which will get reduced, would certainly act as cathode. So the one with higher E naught redox, E naught reduction जिसका ज़्यादा रहेगा, it will act as the oxidizing agent. First of all, the one with higher reduction potential will get reduced. Will act as oxidizing agent, certainly because it gets reduced, will act as oxidizing agent, will act as cathode, will get deposited at cathode in preference. I guess you all remember, cathode is where you have, reduction happening, and out of different cell, which is like zinc becoming zinc plus 2, Cu plus 2 becoming copper. The reason we start talking more in terms of reduction potential is, reduction potential is this the standard, conventional global. The only thing you'll want to see is whether it's getting oxidized or reduced by the charges given, or at times OX or RED given. If nothing is given, so it's only electron potential is going to be reduction potential. Lithium, sodium, potassium, metro L blocker. I've told you all of this. The moment when you come down, the reduction potential will decrease. The one at the top, will be the one which will be the strongest oxidizing agent in freeze-thaw. This will be the strongest reducing agent, and इसका reduction potential will be minimum. In other words, oxidation potential will be maximum. और जितना नीचे आते जाओगे उतना reduction potential बढ़ता जाएगा. हाइड्रोजन का ऑक्सीडेशन reduction potential दोनों तरफ है. So all the ones below hydrogen will have reduction potential positive, and all the ones above hydrogen will have reduction potential negative. So I ended up doing it in a bit of a hurry. If you tell me, I can spend a couple of more minutes, you want me to talk about it in details, I'm willing to do that. Else we'll want to move on. So, electrochemical series, as you move down, reduction potential increases. This is 0. So below hydrogen it's positive, above hydrogen it's negative. I'm going to talk more about reduction potential because that's a globally accepted potential value. The one at the top, being the most metallic, is the most reducing, will get oxidized, will have the maximum oxidation potential, minimum reduction potential. And right at bottom, this will carry on. Fluorine is the one which is most oxidizing, will always get reduced and will have maximum reduction potential. So I wanted to do it in some sense of urgency. I think we're happy with this and we'll want to move on. Now,
Yes,
all the
sir.
values which you are given, for copper, gold, mercury, zinc, are at 1 molar and naturally are taken as E naught values. So somewhere, we felt the need of having a particular way of finding E. Now, when I write product by reactant, you know what I mean. These are going to be the concentrations at the instant when the corresponding E is measured. So, this is called Nernst equation. I've spoken a lot about Nernst equation in my classes, so I don't want to elaborate. Basically, this P by R is another way of writing what's called the reaction quotient. So, this is going to be very, very handy in finding the E of, different systems, half cells, full cells, and, we'll talk about it in form of applications. Naturally, at equilibrium, when the cell would stop delivering current, one way of finding, this Q would become Kc. One way of finding Kc is antilog of. Now this is generally, and I don't know why I'm writing 2 here, because I'm maybe most used to writing 2 here. Antilog n E naught upon 0.059, and there's again such a common result. Kc is equal to 10 to the power n E naught upon 0.059. I think I'm being understood. Anything which you don't understand, you can ask me, but other than that, we'll want to move at some pace. So I think all of this is known to you. This is how you can get Kc, the equilibrium constant, electrochemically. Now the third portion in this segment is Faraday's law. Now in Faraday's laws, and somewhere I need to write all of this is because the relationship delta is equal to minus NFE, which is the change in Gibbs energy. The change in Gibbs energy, or it's also called available energy. It's also going to be called the work done. So many times the term work done could be confusing. Work done is the amount of the energy which is available for a given electric cell delivering current. Naturally, it will be negative if E is positive, and this formula minus energy is going to work. Faraday's law, the first law is going to talk about W1 by W2 is equal to Q1 by Q2. The second law is going to talk about W1 by W2 is equal to E1 by E2. And certainly, eventually, E1 by E2 is equal to W1 by W2. I mean, I'm so sorry for saying Q. You had Z1 by Z2 here, the electrochemical equivalent. Now this would be like Z1 by Z2 is equal to E1 by E2. And you take the second one as hydrogen, and there's such an important result. Z of a particular species is going to be its chemically equivalent to Z of hydrogen, if you remember, all right. Now this is E into 1 upon 96500, which is going to be the amount of hydrogen liberated on passing 1 coulomb of charge. So I think this is understood. The moment I write W is equal to ZQ or ZIT as EQ upon 96500. I remember if Q is equal to 96500 coulomb, E is equal to W. W is equal to E. W is equal to E. I should write W is equal to E rather. Now, naturally, it's going to give me such an important result. 96500 coulomb, which is eventually called 96500 coulomb, which is eventually called 1 Faraday, would be taken as one equivalent, and this will give you one equivalent of everything, as I keep on saying. 96500 coulomb will give you one equivalent of everything. So I think this is the stuff which we want to know in electrochemistry. This is the stuff which you want to know in electrochemistry. Now you can solve all the questions of electrochemistry. Nothing new. If and when required, I'll do some value addition. Time to talk about colligative properties. Now, in colligative properties of solutions, right away, the first equation which comes to my mind is P is equal to some PA plus PB, which is naturally equal to XAPA0 plus XBPB0. Now, remember, this could be written in a particular manner. This could be written as PA0 plus XB minus XA. PB0 minus PA0 XB. If you remember, I told you that this is going to be a particular case where always PB0 is supposed to be more than PA0 is going to make things easier for me. I believe this is more volatile. This is more volatile. And, something like this will give me a straight line where a bivariant plot, when I plot total pressure versus, XB, XB01 would naturally will mean यहाँ पर XA1 है और यहाँ XB0 है. I'm plotting XB के साथ में, this is y plus y is equal to mx plus t. So when this is like y is equal to mx plus c, the y coordinate is PA0, and naturally this is generally taken below PB0. This is going to be the slope. This is for xp is equal to 1, which is for pure B. This is for pure A. And these are going to be the plots for PB and P. So this is for PB is equal to XB PB0. This is for PA is equal to XA PA0. At any point of time, if this is the value of PA and if this is the value of PB, if this is the value of PA and if this is the value of PB, when you add this P would be equal to PA plus PB. So this is what I do tell you. In a particular case, if you are completely oblivious of the results and you want more help, I can share the video with you. But this is what I want to begin with. P is equal to XAPA0 plus XBPB0. This could also be written as PA0 plus PB0 minus PA0, which will be the slope. XB, I would want you to remember this right away. And if you remember, I had given you a result between the vapor composition and the liquid composition. This certainly is the liquid composition in terms of Raoult's law. And I tell you, if you have XBPB0, it will be the same as XB prime into total pressure, where XB prime would be the vapor pressure in the vapor form. This will be the partial pressure. This will be the mole fraction in the. This is the mole fraction in the vapor form. Because I can always write partial pressure is equal to mole fraction in total pressure. And this is such an important result. XB prime is equal to XBPB0 upon total pressure is XAPA0 plus XBPB0. This is something which you'll always want to remember. This can come handy. And I draw the liquid composition curve, the vapor composition curve. I'm not willing to do it right now because I don't see it coming in the board exam. But when the time is right, troughs and all, those are going to be very relevant for JEE and all. So after this formula, this is a formula which I want you to remember. An outcome of this is when you have a non-volatile solution and P0 minus PS upon P0 is taken as small n upon small n plus capital N, which is generally taken as a small n. And if you don't want any compromise, P naught minus PS, if you take PS here, this is not equal to approximately n. This is exactly equal to small n by capital N. So, the formula is about finding the PS. Maybe, a small n by capital N will be a compromise, but if it's about finding the molecular weight, so many times it's used to find the molecular weight. So, this is exactly equal to small w by small m upon capital W by capital M. All these small letters for the solute, capital letters for the solvent. So, I think I have done this with you. This is exact relative loading of vapor pressure. This is not exact loading of vapor pressure. Instead of P naught, you take PS here, but this will give you clinically the most correct value of, suppose, small m, which is generally the problem in most of the cases. Del TF is equal to Kf into I into molality. Del TB is equal to Kb into I into molality. I is equal to 1 plus n minus 1 alpha for a dissociation, and I is equal to 1 plus 1 by n minus 1 alpha. This is for dissociation, and this is for association. So molality is number of moles per 1,000 gram of the solvent. This would always come in this manner. If you want molality, if this is the mass in grams, weight upon molecular weight, number of moles. Capital W means the weight in grams of the solvent, naturally water, number of moles per gram into 1,000. So this is something which I've always wanted people to remember, firsthand, fundamentally. If you have a problem, in any of the results, you can speak to me to share the videos. But again, I is equal to 1 plus n minus 1 alpha for dissociation, और association में उल्टा कर देते जब डाइमर आइमर बनता है. डाइमर के लिए मैं बोलता हूँ इसका वैल्यू याद रखना चाहिए. I is equal to 1 minus alpha by 2. ठीक है, ये सारा वैल्यू याद रखना चाहिए. ठीक है. I hope I'm being heard properly. बच्चे लोग हाँ ना बोलो.
Yes, sir.
Time to move to kinetics. Now in chemical kinetics, result number 1 is rate is equal to K reactants to the power N. Is basically law of mass action. This is called rate constant, which will have a unit of moles per liter to the power 1 minus n per second. This is the amount of concentration in molarity, it's moles per liter. Rate is moles per liter per second. Now, we talk about order of the reactions and all, but before that, we talk about K is equal to A into e to the power minus EA upon RT. I know you know about this activation energy, the exponential stuff and all, so I'm not going to tag all of it. It's called Arrhenius equation. A couple of things that I want to add to your knowledge. E to the power minus EA upon RT is very popularly called as the fraction of molecules having energy equal to or more than the activation energy. So again, it's a very popular term. You'll want to take a note of it. The ratio EA by RT is called Boltzmann factor or Boltzmann constant. There are such things I've already told you. So these are a couple of things I want you to take note of. So many times the question is find the fraction of molecules having energy equal to or more than the activation energy. So this is going to be the ratio. But चलो हाँ ना बोलो. And then taking log on both sides, log K is equal to log A minus EA upon RT, and 2.303 log K करके 2.303 लेकर के, in natural logarithm. Eventually, in form of log K upon 1 by T. So this is log K along the y-axis, 1 by t, because the rest are constants along the x-axis, and the slope is going to be minus a by r. ln a would be the y coordinate, and the slope would be minus e by r. Naturally, if the same is using natural logarithm, the slope would be minus e upon 2.303. I've told you 15 times, just make sure you keep e and r in the same unit. You keep e and r in the same unit. For two different temperatures, log K2 by K1 is equal to E8 into minus T1 upon 2.303 R. T1, T2 is such an important result. We'll be using it in different questions. I think this is fresh in everybody's mind. And for a catalyst, log K prime by K is equal to EA minus EA prime. Rather, EA prime minus EA upon 2.303 RT is when you have a process which is catalyzed. The prime values are using a catalyst. And then first order, second order, how pH values would change. I think is something is known to all of you. When the time is right, maybe I'll share some notes of graphs with you. But I don't want to go into the mathematics of first order, second order, third order conditions right now, because that is very basic calculus. मैं थोड़ा सा ना और cases parallel और consecutive का कराऊंगा. Yet again when the time is right. और मैं देखता हूँ अगर मेरे पास एक graphical representation का pic है ना, I'll send it over to you so that you can relate to it. And for the time being, I think this much of theory is going to help you in solving all the questions. What I'll do is I would rather want you to look at the 3 question papers I've given you so far. So ISC का 2024 का paper, ISC का 2023 का paper. ISC guys have an advantage. They can use calculator as well. और CBSE का जो मैं सेट 4 और सेट 5 दिया हूँ, सेट 4 और सेट 5 दिया हूँ, I believe सेट 4 और सेट 5. इसका जितना भी न्यूमेरिकल्स है ना, ये सब तुम लोग देख के रखो. मैं देखता हूँ सारा न्यूमेरिकल्स नहीं होगा तो मैं एक बार जल्दी से इवनिंग में टाइम निकाल करके सॉल्व करा दूंगा. And keep solving the board exam questions. Let me know if there is a doubt. I thought that we'll have enough time to solve some questions, but I think this was an important exercise that we go past all of it. मैं एक pick notes का भेज दूंगा जहाँ पर सारा ग्राफ होगा kinetics का. Anything which you want me to do, anything else that you want me to do, because next I see myself solving some problems with you. I would give you some time to attend those questions and maybe do that in the second half of the day. Chalo, sir, stay happy, stay healthy. Catch you in the evening one more time. ठीक है, चलो, bye bye.
Bye, sir.